So this week we talk about integer programming, which is actually built on the linear programming. So we add extra constraints for your problem. So far we have only looked into the problems with continuous decision variables. So for the general LP problem, so actually in many cases, the fractional values are not applicable. For example, the production quantities. So what should we do? Of course, you can do rounding, but the rounding may not always be the best solution. So that's actually commonly treated as an integer programming problems by constraining your decision variables to be integers. So here we can see we are talking about 2 types of integer variables. So you can see your decision variables general integer, for example, is equals to 1, 2, 3, 4, can also be binary variables. So that means the value can only be 0 or 1. So a linear programming problem, including integers, normally is called integer programming models. If your model includes both integer decision variables and continuous other type of decision variables, so that's actually called mixed integer programming. So in the literature, it's often seen as a MIP. So we use a very small example to show what is integer programming models. So now we have a general linear programming model. We only constant decision variables are non-negative. Then if we solve this LP model, we got optimal solution, which is 10.5 and 7.5. Now, if we restrict the solution to be integers, so what if we want the solutions to be integers? Then, of course, you can solve this model in the Excel solver. So now we actually use this case to explain how to solve the integer programming models. So from the LP to integer programming, you only add one extra constraint. So here in this example, we can see we have x1, x2 are integers. So now if we think about solve the LP model graphically, then you can think about the feasible region. So of course the original constraint also hold, and the non-negativity constraint also hold. So your decision feasible region still be the yellow area. However, the x1, x2 has to be integers. So basically, your decision should just be some points inside this yellow shaded area. So we can see these feasible solutions. So all these black dots, they're actually called feasible, for example, this actually is called feasible solutions for your problem. But we are interested in the maximum objective values, optimal solutions. Obviously, previous the corner points will not work, and then if you move your level the objective function line, so it's actually not necessary to find the optimal solution. So we need some special method to efficiently solve this problem. Now let's see, if you round up your optimal solution to be 11 and 8, so then you actually get a higher objective function, which is greater than 61.5. However, you can see this point actually is not feasible. It's actually outside your feasible region. So this is not the solution. So I have to search for other solutions. So now if we try to move the point, the x2 solution 1 unit smaller, it become 11, 7. They may actually reach this point on the boundary. So now you actually have a slightly smaller objective function value for the new solution. So what if you actually reduce the value for x1 for 1 unit, you get a solution 10, 8. Then your objective function is 6, 2. And now you can see actually this solution is not feasible either. So this actually kind of random searching for optimal solutions by round up or down your original linear programming optimal solutions are not that efficient or reliable. So if you continue to try other solutions, for example, to try 10, 7, this point actually is feasible, but objective function seems low. And then, so if we try this, so try a new solution 9, 8. So this is also feasible, and the objective function value also lower. Actually, it's quite inefficient to search for the solutions go around this corner points. Then there's actually no right direction for you to solve this problem. So we need a structured method. So to solve the integral programming models, we have a method called branch and bound method. So we try to explain this method in the next few slides. In this slide, there is a mistake, so I should add a new branch x1 greater than or equals to 11. Then now we can explain what happened here. In order to find the feasible optimal integral solutions, so we can actually split the feasible region into two areas. Then you form two problems, new integral problems, one with a constant x1 less than or equals to 10, one with a new constant x1 greater than or less than 11. So this is problem 2, this is for problem 1. Now if you solve the LP relaxation of problem 1, so basically in this area, then you can find the optimal solution in this corner, which is still not completely integral. So in order to find the integral solutions, you need to further do branch and bound. So from your original problem 1, then you generate new problem 1.1 and 1.2 by add the new constant. Now you add a new constant x2 greater than or equals to 8, which is the red shaded area, and x2 less than x7, which is the yellow area in the corner. So if we continue to think about to solve the problem 1.1, you actually should have the optimal solution in this corner. So you got a solution 10, optimal solution 10 and 7. And then for the problem 1.2, you have different corner points, you do not reach the integral solution. Then you continue to do branch and bound for your problem 1.2 by adding new constraints. So here you actually can continue to split your problem by adding the constraints in the x1 and until you find all the small areas. So in this way, it's rather efficient because, for example, for the problem 1.1, you actually stop searching, and then so for problem 1.2, continue searching, and problem 2, continue searching. So in this case, you actually still save a lot of time to check all the possible solutions. So the method until you exhaust the search, find the optimal solution in the end. So that's actually a branch and bound method. A cutting plane method is also commonly used to solve mixed integer programming. So in our course, we do not go deep into this method. So the general idea is you just cut off the areas which does not include any integer solutions. So you can see the lines drawn in this figure. This graph actually shows how will you cut off the not necessary areas until you find all the optimal integer solutions. So actually, based on this different method, the commercial softwares also provide the solution method for the integer programming models. For example, our Excel solver can solve the integer programming models as well. So we do not explain how to do that in this video, but we do have several examples in the Zoom meeting. We're going to address them. I will show you how to do how to solve the integer programming by Excel solver.